Okay, good morning, students. I want to make sure that everyone understands exactly where we're going this week. And so we're going to walk through, whether or not I'm in class or not, walk through measurement, precision, and accuracy, making sure that we can connect back to our coin lab. So, this week, we are celebrating Heroes of Latin America as we bring up the second half of Hispanic Heritage Month. And yes, that's Bad Bunny. We shout Bad Bunny, who will be presenting at the upcoming Super Bowl, but also because Bad Bunny is a hero of his own when it comes to climate change. And we'll talk more about that in the days to come. All right. So, what is Latin America? There are 33 nations that make up Latin America and South America, Central America, and the Caribbean or North America. And so, we will spend some time thinking about scientists and issues that impact Latin America for this upcoming project. It is grounded in the Sustainable Development Goals, which were developed by the United Nations as a global initiative to draw attention to challenges engineering and science that we need to address all of these things, starting with the people, then moving to the systems, and then elevating to the idea that this is going to promote world peace. So we didn't get a chance to talk about all the things, but I really want everyone lab. We were looking at hmm, calculating density of pennies, but we were doing it graphically for our class. And so what that means is we were gathering information and looking through it. Here we go. And I just really need to make sure that everyone understands what hold on one second. I need to make sure everyone understands that when we gathered this information, it was with the intent of using it to graph density, not to calculate each individual mass and density, excuse me, mass and volume, or each individual density. So, how did we do this? We took individual masses, we took the masses of individual coins. Excuse me, we took the mass of one coin. Then we put stacks together, stack 1, 2, 3, 4, 5, to represent a sample of coins. You should have a data table that has those data. What's the mass of each stack of coins? What's the volume of the stacks of coins as it was added to the graduated cylinder? I have added here for clarity a column that says how many coins were in each stack. You did not have to have equal stacks across the board. As a matter of fact, it's much more powerful to actually say, oh, wait, they're not the same amount. And do I get decent results either way? The reality of it is, you're not always going to have the same amount of anything in a sample. So, to make it a little bit more realistic for each stack, I have indicated the number of coins in each stack, what the mass of each stack was, and then subsequent volumes, making sure to note what the initial volume of water in the graduated cylinder was, which was 52.5. Now, when I look at that, I have to now make sense of it. If the original that is in my graduated cylinder, if I had a graduated, oh, that's lopsided, but whatever. If I had a graduated cylinder with just water in it, that was 52.5. That was my initial volume, 52.5 milliliters of water to begin with. Once I added coins to it, that means that the volume was higher. So it went up, let's say here, after adding that first stack. So here are my coins. I've added my first stack of 3 coins. My volume went up to 54 milliliters. Well, if it started at 52.5, adding the coins to 54, that means the volume of that first stack of coins with a mass of 15 was 1.5 mils. Okay, so how did I get this second reading? This second reading of 34.9 is the sum of stack 1 and stack 2. When I add the second stack, it went from 54 to 56.5. Well, I still have to remember that 56.5 started at 52.5, and so that is why the volume is 4. Without circling all the things, this is how I generated this chart. This is my final data chart. Oops, that's terrible. This is my final data chart for all 5 stacks of coins. Stack 1, stack 2, stack 3, stack 4, and stack 5. So that the cumulative mass of all of my pennies is 129.8, and the cumulative volume of all of my pennies is 14.5 taken all together. So once I have that, now it's time to graph it. Graphing, you each have graphing paper or should have access to graph paper. Graphing this, your volumes are on your x-axis and your masses go on your y-axis. Masses in grams. Volume was in milliliters. So on your graph paper, you're going to graph your final data so that when I look at the range of information, I am not starting at 0. I'm starting at 15, and I go from 15 to about 130. So, I'm going to go by 20s, 20, 40, 60, 80, 100, 120, up. I know up a little bit further because this would be 140. So if this is 20, just for what I have done here, I go from 20 to 140, and I'm good to go. I go from 1.5 to 15. So I'm going to say 2, 4, 6, 8, 10, 12, 14, 16. Now, again, you will use the actual graph paper that has the grids drawn. I'm just impromptu drawing it for the sake of this video. So 1.5, 15. Well, this is about 1.5, 15. There you go. There's my first point. 4, 35. Well, I know that's 40, so it's a little bit lower. 6.5, 60. 9.5, 90. 14.5, 130. Now, those are my points. You have to draw a line of best fit. Okay, this is not going to be perfect, but there you go. Pretend that's a straight line. That's my line of best fit. And then once I do that, I can find the slope. When I find the slope, I use 2 points that are on the line. Okay, to find the slope. So finding the slope is, by definition, the difference in the y's. So y2 minus y1 divided by the difference in the x's, x2 minus x1. When I find the slope, wait a minute, hold up. What am I actually doing? The slope on this graph would be the difference in y's. Wait a minute, that's a mass differential divided by the difference in x. Oh, wait, that's a volume differential. So when I find the slope, I'm actually calculating the density of those pennies. Well, here's the good thing. I actually did it. I actually completed this calculation using Excel spreadsheet. So when I look at the Excel spreadsheet, when I look at the Excel spreadsheet, I can just go there. Wait, hold on. Let me go to the source. Here it is. When I go to the Excel spreadsheet, I see that it's 8.99. That is my slope. And to make it also very clear for everyone, here is the original data. So this is the original data. This is the simplified data. And here is that graph. So I did the same thing for nickels that I did for pennies because I know we had both coins in the room. Here is the information for pennies. The slope for the pennies is 6.99. The slope for the nickels I got was 8.99. And now it's time for me to do my percent error analysis, which you need to include in your analysis and conclusion. So for you, what is the identity of coin one and coin two? I gave it away. How do you know? We can look at the data, the average data from the US Mint. Keep in mind, the US Mint is the place where all of the standards are set for coins. So the penny should have a diameter of 1.905 centimeters or 19.05 millimeters. It should have a mass of 2.5. I could compare that. The nickel should have a weight or a mass of 5.00 grams and a diameter of 21.21 millimeters or 2.121 centimeters. Again, there's a lot of significant digits there, but we can figure it out. All right, so this information allows us to not only identify the identity, but give us details about accuracy. And we can do that, but wait, we have to compare because you were supposed to compare your data to other members of your group. So how do you make a comparison? In order to make the comparison, you all need to get an average mass for your table. So an average mass for your table, go ahead and find that. And then the density, average density for the coins at your table. Then finally, do your own percent error calculation in your lab notebook. Percent error again is the absolute value of the difference between the experimental or what you got value and the standard value, what the US Mint says is supposed to be, divided by what the US Mint says is supposed to be times 100. So when I did mine, I'm like, "Ooh, I'm really close." Because according to the data, the density of copper is 8.96. The density of zinc is 7.14. When I look at my data, I got a density for the penny, a density of the penny of 6.99. So my 6.99 grams per mil density suggests that my penny is mostly zinc. And well, this is density of penny. That makes sense. I got 8.99 grams per mil as the density of my nickel. Very close. Well, here's the interesting thing. When we go back and look at what the data says, the density of pennies, or excuse me, the composition of pennies, they are mostly zinc. So that makes sense. When I get ready to do my calculation, I sort of say, oh, okay, what do I actually have here? I would say for the penny, 7.14, what I actually got minus, excuse me, what I expected to get minus 6.99. And again, the units in this case don't matter because we don't need, they would cancel out. 7.14 grams per mil is what we expect to be the density of zinc. So I would look at the difference between 7.14 and 6.99. When I do this, then I'm going to multiply by 100%. So this is 0.15 divided by 7.14. 0.15 divided by 7.14 is 0.021. When I multiply that by 100, I get 2.1%. So for my penny, I got 2.1% error. Very good. Typically, we want to be within 5% to say that we have accurate measurements. And so that's what I got. That is what I got. I could do the same thing for my nickel, where the difference is 0.09 divided by what I expected to get, 8 point, I'm going to go with 8.95 or 8.9, yeah, 8.99 and 8 point, yes, there you go. And so 0.09 divided by 8.95 equals 0.010, which means I have even better data for my nickels at only 1% error. All right, this is what you are going to do. Hopefully you won't have to use this video because I'm going to be there post-testing, but if you do, you'll be fine. I'll see you soon.